A beam of white light enters a prism, and out the other side comes a rainbow. It feels simple, but the real explanation is much stranger than most textbooks admit. The standard story says light slows down in glass, and because different colors slow by different amounts, they bend by different amounts too. That story is useful, but it quietly hides the most important question: why would light slow down at all? And even the phrase slow down needs care, because in a material, the frequency stays the same while the wavelength gets shorter. The index of refraction, usually called n, is just the ratio between the speed of light in vacuum and the phase velocity in the material. For ordinary glass, blue light usually has a higher refractive index than red light, so blue bends more strongly. So the real goal is not to memorize a rule. It is to discover the mechanism that makes the rule happen. Feynman's strategy is beautiful. Stop treating glass as a mysterious block and start thinking about the charges inside it. Imagine the material sliced into many ultra-thin layers, each one perpendicular to the direction the light is moving. Now exaggerate the effect of a single layer. Instead of stopping the wave, that layer gives the wave a tiny kick backward in phase. Phase is just the horizontal position of a wave cycle. A phase delay means the peaks show up a little later than they would have otherwise. If one layer gives a tiny delay, then many layers give many tiny delays, and those delays add up. As the layers become denser and each delay becomes smaller, the jagged picture smooths out into something that looks exactly like a slower wave. That is the first key idea. Refractive index can be understood as accumulated phase delay. So now the question becomes sharper. What gives a single layer that tiny phase delaying power? To answer that, we have to remember what light is: an oscillating electric field moving through space. When that electric field reaches an electron bound inside a material, it pushes the electron back and forth. And a moving charge does not stay quiet. A charge that accelerates radiates its own electromagnetic wave. That means the incoming wave shakes many electrons, and those electrons send out many secondary waves of their own. The material is not really blocking the light and relaunching it later. It is continuously adding new waves on top of the original one. So the whole problem becomes a superposition problem. Add the original wave to all the tiny reradiated waves. Feynman focuses on one thin sheet of charges and asks what net wave that whole sheet sends forward. The wave from each individual charge reaches the forward direction with a slightly different path length, so their phases are not identical. When you add all those contributions together, most sideways pieces cancel, and the forward contribution survives. And remarkably, that forward reradiated field ends up 90 degrees out of phase with the driving field. That 90-degree lag is the heart of the story, because adding a small lagging wave does not change the wave much in size, but it does nudge its phase backward. So one sheet of charges produces one tiny phase delay, and a thick material produces many of them in sequence. At this point, we understand why a medium can change phase velocity, but we still need to know why the amount depends on color. For that, Feynman models an electron inside the material like a tiny mass attached to a spring. The incoming light field is the driving force, and the electron's binding to the atom provides the restoring force. This is the driven harmonic oscillator, one of the most important models in physics. If the driving light oscillates very slowly compared with the electron's natural resonance, the electron follows along almost in step. But as the light frequency gets closer to the natural resonance, the electron response gets bigger and more phase-shifted. That is exactly like pushing a child on a swing. If your timing is off, the response is small. If your timing matches the swing, the motion grows dramatically. The reradiated wave depends on that electron motion, so the phase and strength of the reradiated wave also depend on frequency. That means the phase kick per layer is not a fixed number. It changes with color, because different colors drive the charges differently. In many transparent materials in the visible range, blue light gets a bigger phase delay than red light, so blue ends up with a larger refractive index. Now, the prism finally feels less mysterious. White light contains many frequencies, and each frequency accumulates a different total delay. And once different colors have different refractive indices, Snell's law automatically sends them on different paths. There is also a better reason for bending than the tank analogy. At the boundary, the wavefront has to stay phase-matched across the surface. When the phase velocity changes at the interface, the wavefront pivots, and the ray, which is perpendicular to the wavefront, pivots with it. There is one more subtlety that matters a lot. The refractive index usually describes phase velocity, the motion of the crests, not the speed of information. If you send a short pulse through a medium, the pulse envelope travels with the group velocity, which can differ from the phase velocity when the material is dispersive. That is why refractive index can even dip below 1 in some frequency ranges without violating relativity. For example, X-rays in matter and electromagnetic waves in plasmas can have a refractive index slightly below 1. What matters for causality is not whether a crest moves faster than c, but whether usable information or energy does. Modern optics pushes this even further with slow light experiments, where carefully engineered dispersion can make group velocity dramatically smaller than c. Some materials also show birefringence, where the response depends on polarization and direction, so one incoming beam can split into two. And in metamaterials, engineers arrange tiny structures to create exotic effective refractive indices, including negative refraction. Researchers are still extending these ideas today. In 2025, physicists reported negative refraction in atomic array systems without traditional metamaterials. But none of this means photons are literally crawling between atoms like tiny marbles moving through syrup. The better picture is coherent scattering. Matter keeps adding a carefully phased secondary field to the original field. In the quantum picture, the language changes, but the macroscopic result is the same. The medium alters phase through its interaction with the electromagnetic field. So when we say light slows down in glass, the most honest translation is that the combined wave accumulates phase delay as it passes through the material. And when we say blue bends more than red, the honest translation is that blue drives the charges differently, so blue accumulates a bigger delay. That is why the rainbow from a prism is not a coincidence. It is the natural consequence of how matter responds to different frequencies. Once you see it this way, the refractive index stops being a mysterious number and becomes a measurable fingerprint of a material's microscopic response. And that is the deeper answer to Feynman's question. Light appears to slow because matter keeps nudging the wave behind, layer by layer, all the way through. So next time you see a prism, imagine billions of electrons being driven, reradiating, and quietly sculpting the wave into a rainbow.